Okay, this reaction asks us to figure out delta S, delta H for the reaction, enthalpy and entropy, then decide whether it's spontaneous or non-spontaneous. And if sometimes spontaneity depends on a condition, what would that condition be? Reactions can be always spontaneous, always non-spontaneous, or sometimes spontaneous. And so we have to figure that out. We're not interested in reactions that are never spontaneous because they don't ever go forward. So we would only be interested in reactions that are either always spontaneous or can be made spontaneous under certain conditions. And so in order to do that, we need to know Gibbs free energy. Delta G is delta H minus T delta S. And so in order to remember that Gibbs free energy is inversely proportional to the change in entropy of the universe. If the change in entropy of the universe goes up, then a reaction or a process is said to be spontaneous. If the change in entropy of the universe goes down, that process is non-spontaneous. And so delta G is inversely proportional. So when delta G is negative, the entropy of the universe is increasing. And so that's a spontaneous process. So in order to figure out delta G, of course, we're really thinking qualitatively here, not quantitatively. We want to look at the sign, not the values. And so we can use the equation once we predict the sign of delta H and delta S to predict the sign of delta G. So in order to figure out delta H, we're going to look at two different things. We're going to look at the number. One thing we're going to look at is the number of sigma and pi bonds. Pi bonds are higher energy than sigma bonds, so all else being equal, the fewer pi bonds, the lower the energy. And so we can predict whether delta H is negative or positive based on that. And the other thing is that we typically say when you make bonds, you gain energy. When you break bonds, you spend energy. So making a bond would then be representative of a decrease in energy. So let's sort out delta H for all of these reactions. We can count all of the bonds, but what we need to figure out is that we want to look at the number of sigma and pi bonds. So let's count the number of sigma bonds. So from the hydrogens, I've got 1, 2, 3, 4, 5, 6, 7, 8 hydrogens. And that means those are all sigmas. Then 1, 2, 3, 4, 5. 8 plus 5 is 13 sigma bonds. And you see that I have 1, 2, 3 pi bonds. In this one, I have 2 pi bonds, and let's count all the sigma bonds. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. I have 14 sigma bonds. And so you see that I had a net increase in the number of sigma bonds. That net increase in the number of sigma bonds means it's a lower energy situation. So the delta H is negative. Now let's erase those marks so we can get a better look at it. And then let's sort out what do we think about entropy. Well, in the reactant, the structure is not a ring. And in the product, the structure is a ring. And so a ring is more constrained than something that's not a ring. So that represents a decrease in entropy. Okay, so delta H is negative, delta S is negative, and so let's get out our delta G formula and sort that out. So if I have a negative value here and a negative value there, what will the value of delta G be? Well, a negative, and this is going to be positive, right? Because negative times a negative, bam, that becomes a positive. So we're combining through arithmetic a positive and a negative number. Okay, we don't know the values of delta H and delta S, so what does that mean as far as delta G is concerned? Well, it means it could be either positive or negative. All right, so we don't know if it's spontaneous or non-spontaneous unless we know the conditions. How do we make the reaction spontaneous? Well, we need the reaction to be we need delta G to be negative. And we see that the delta H term is the negative term, and the delta S times negative delta times negative T, that's a positive term. So in order for this entire value for delta G to be negative, this value has to be small. right, compared to the negative value. How does the delta S value stay small? Well, it really, what does it depend on? And this is going to be the answer every time. It depends on the temperature. How do I make the T delta S value small? That's at low temperatures. So this one is spontaneous at low T. Okay, let's take a look at the next one. So I'm going to be in the same situation as before, as far as the bonds with hydrogen not changing. So I'm not going to even count them this time. But what I will count is I've got 1, 2, 3 pi bonds there and only 1 pi bond there. So remember that pi bonds are higher in energy than sigma bonds. So this process is endothermic. It represents an increase in energy because the net number of pi bonds increased. Now, what about delta S? Let's erase this marker so we can get a good look. I went from a ring to something that's not a ring. Not only is it not a ring, it's 2 different particles. So 2 different particles have many more degrees of freedom than a 1 particle that's a ring. So the entropy is also increasing. Okay, so let's take another look at delta G. Well, what's going on here? I've got delta H is positive, and I'm going to subtract that from another positive number. And so if I think about multiplying a negative times a positive, I end up getting a negative value. So the quantity T delta S is negative T delta S. That quantity is negative. So how do I want delta G to be negative? So how does, and when I'm combining a positive and negative number, it could go either way. And so how do I figure out when this reaction is spontaneous? Well, I want that negative term to be as large as possible. So how do I make that negative term as large as possible? T needs to be large. T needs to be large. So this one is just like the other one, but conversely, it's spontaneous. Instead of being spontaneous at low temperature, this one is spontaneous at high temperature. All right, let's take a look at the next one. So the next one is that situation where I said we're actually forming a bond. And so forming a bond with all else being equal is going to be a negative change in enthalpy. But we have 2 particles, water and a cation, coming together as 1 particle. So that's also a decrease in entropy. So we already understand what's going on with the situation when enthalpy is negative and entropy is negative. We know that this is spontaneous at low T. Okay, that's it.